Hello again. This section is going to be a little bit backwards compared to some of the others because the way this section works is a bit backwards. The intent of this section is to be able to graph rational functions, but I think that's better done in calculus because they have better tools in calculus. So we're going to work less on building the graphs than on identifying the graphs. But to summarize, let's start with a function. Rational function x plus 2 times x minus 1 all over x times x plus 1. And last time we identified how we were going to find asymptotes. If we go ahead and multiply this out, we're going to get x squared plus x minus 2 all over x squared plus x. But when we're graphing things, we usually want a couple of important pieces. First, we want, well, what you do first doesn't matter a whole lot, but I'm going to do x-intercepts first. And we find these by setting the top equal to 0. Generally, if you want x-intercepts, we want y to be equal to 0. But since we have a fraction over here, our solution to y equals 0 is when the top is equal to 0, because 0 divided by a number is still going to be 0. But when we get to the second step here, when we're looking for vertical asymptotes, we're going to want to compare these with the x-intercepts to see if we have any deletions for the asymptotes. So in terms of our function, we're looking at x plus 2 times x minus 1 equal to 0, which gives us the solutions x equal to minus 2 and x equal to 1. Next up, we'll have the vertical asymptotes. That's when we set the bottom equal to 0. Because we get vertical asymptotes when we divide by 0. So we're looking at x times x plus 1. Let's see, and that's equal to 0, which means we get x equals 0 and x equals minus 1. Now if we look, we compare these with the x-intercepts, none of these are repeated, so I don't have any weird holes to worry about. And then what we have next is, well, we can look at the y-intercepts. We just set x equal to 0, and whatever number we get, we get. But that doesn't work for this problem because x equal to 0 is one of my vertical asymptotes. So I'm not going to have a y-intercept for this problem. And finally, we can look at horizontal asymptotes. Oops. Now this one, I've got the same power top and bottom. So I just use the coefficients of the biggest parts. And that means I'm going to have a horizontal asymptote of y equal to 1. Now we can collect this information and provide something of a rough sketch of what our graph is going to look like. I can squeeze that in right over here. I have an x-intercept at 1 and minus 2. I have vertical asymptotes at 0, so that will be the y-axis, and at minus 1. So I'll leave a dotted line there. I didn't have a y-intercept because that's one of my asymptotes, and my horizontal asymptote is going to be y equal to 1. So that goes across here. So what I expect this to look like, and you can try with a calculator of some kind. Oops, I crossed my vertical asymptote. A vertical asymptote at 0. And then what should happen, because I don't cross the x-axis in between these two things, because I only had 2 x-intercepts, is I'm going to have some kind of a U-shape in between my final 2 asymptotes. I can plug in a number to see if it's top or bottom, but I know from other problems that this is just going to be up here. And the reason I know is because these asymptotes, I could say they have multiplicity 1. I'll show you what that means on the next example. I should have probably started with a step 0 here. We get this information when we're looking at the vertical asymptotes, but the domain is wherever the denominator is not 0, wherever bottom is not equal to 0. So since my vertical asymptotes were 0 and -1, my domain goes from -infinity to -1, everything between -1 to 0, and everything after 0 to infinity. But having the domain, at least for me, doesn't help me graph things as much as this other information does. So let's line up a picture here. This is what I meant by going backwards. Here I have a graph of a rational function. We don't know what rational function it is, but we can look at the information we have available. Immediately, we see we have a horizontal asymptote here. That's at y equals 1. We have a vertical asymptote here. That's at x equal to 4. So let's list that information. We had a horizontal asymptote, y equals 1, vertical asymptote, x equal to 4. Let's see what else we can see. Oh, it looks like I missed another vertical asymptote. We see here at x equal to 0, the y-axis, my curve, or my function, treats it like an asymptote. It goes way straight down and it goes way straight up. So that's another vertical asymptote for us, x equal to 0. Now what else do we see? Well, we see we have x-intercepts. I've got one here at -2, at 1, and at 3. Now, since we had a vertical asymptote at x equals 0, we're not going to have a y-intercept with this one either. But what we can see is, well, there aren't any other obvious looking domain problems. I can see what happens going up in this direction by trying to zoom out and failing to zoom out. There we go. But we see that it just goes up forever. So let's try to collect this information. The biggest parts are the x-intercepts and the vertical asymptotes, because those are going to give me the bulk of my rational function. I'll call this one G. But what I expect to see is from the x-intercepts, x equals -1, x equals 2, and x equals 3. That should give me factors x plus 1, x minus 2, and x minus 3. And then on the denominator, where I get my vertical asymptotes, should give me x and x minus 4. And then what comes last is the horizontal asymptote. All I really do once I've set this up, unless my horizontal asymptote is 0, so I'm going to write here this is not equal to 0, so I will multiply by my horizontal asymptote. Because if I had a horizontal asymptote of, say, 2, I would multiply by 2, and that would be because when I multiplied out all of the parts of my expression, or my function, I would have, let's say I have a cubic on top, I might have 2x cubed on top, and then regular x cubed on the bottom. But actually, now that we mention that, we see here we have 3 x's on top, 2 x's on bottom. If we were to multiply this out, we would see that the top degree is 3 and the bottom degree is 2. Now, according to my rules for horizontal asymptotes, that would say no horizontal asymptote. But I know from my graph that I have a horizontal asymptote at 1, which means I must be missing a factor in the denominator. So let's go back to our graph. And we see that we had 2 different vertical asymptotes. There's one here at 0, and the graph goes in opposite directions there. But there's another here at 4, and the graph goes in the same direction there. They both sides go straight up. Now what that means is it actually works just like multiplicity for roots. If I have an odd power root, then it goes through the x-axis, positive on one side, negative on the other. If I have an odd power for an asymptote, then it will be positive on one side, negative on the other. So for my x equals 0 asymptote, I go to negative numbers on one side, and I go to positive numbers on the other side. So here at my x equals 4 asymptote, I go to positive numbers on both sides. So what I should have is that asymptote doubled up. So I should have a final answer, x plus 1, x minus 2, x minus 3, all over x times x minus 4, and that is squared. An odd power for an asymptote means that the graph goes in the same direction on both sides. Now, whether that's positive or negative will require some additional checking. Maybe just have to test some points. In calculus, you just do a limit to check what happens, but we're going to stick with going backwards for ours. We have a graph. It goes up on the same side. It goes up on both sides, same direction. So I should use an odd power for my vertical asymptote. Now, what did I just say? Did I say odd? You should have an even power for your vertical asymptote because it goes up on the same direction, both sides. I'm going crazy. I could add my times 1 for my horizontal asymptote here, but it was just 1, so it won't change my problem. Now, when I'm looking at the asymptotes and the intercepts, I only know whether I have even multiplicity or odd multiplicity, but if you're constructing an equation based on a graph, the safest bet is to just use the simplest expressions possible, or the lowest degrees possible. So let's see if I can make both of these fit on here. That's my g of x that I constructed that I should have. And let's see what I actually put in here. And what do we find? We find that I completely mislabeled my x-intercepts. So let's go ahead and fix that. Let's see what my graph is supposed to look like. I didn't label these correctly. I'll have an x plus 1, and I wrote x minus 2. Oops, where is that going? That's better. So let's see if we can line this up now. I have my vertical asymptotes at 0 and at minus 4. I squared it to make sure they go up in the same direction both sides. That's what I have in the denominator up there. And on the top I have x plus 1, x minus 2, and x minus 3 for my x-intercepts, minus 1, 2, and 3. So let's try that again with a different looking function. I have another one lined up here. It looks a little bit less busy than the last one. But what do I have here? I have a slant asymptote, not a horizontal one. I've also got over here a labeled hole in my graph, so that's going to affect my final answer. But let's see, I've got a vertical asymptote here at x equal to 0, and it looks like I have x-intercepts at plus 2 and minus 2. So let's label this. Let's see, we found x-intercepts, x equal to 2 and minus 2. We had a vertical asymptote at x equal to 0. Let's see what else we have. Since I have a vertical asymptote at x equal to 0, I won't have a y-intercept. That's okay. But what about this slant asymptote? Looks like it's a straight line that goes up at a slope of 4. It goes up 1 and over 4 repeatedly. So let's say my slant asymptote is y equal to 1 over 4x. Or I could say x divided by 4, whichever you prefer. But I have a y-intercept of 0 for that asymptote. And I also have a hole at x equal to 4 and whatever the y value is that goes with that. Whoops. So somehow, probably at the very end, we're going to fix my function so that it's going to be undefined at x equal to 4. So that's one of the places where worrying about the domain can come in. Domain is minus infinity to 0, 0 to 4, and 4 to infinity. So let's see, let's call this one h of x. We're going to be looking at the x-intercepts. Those go on top. That's x plus 2 times x minus 2. We have a vertical asymptote, x equals 0 on the bottom. So that's just x down there. And we have a slant asymptote of 1 over x. So this is already set up so that I've got x squared minus 4 all over x. And now if we do long division, we're going to get a whole part and a remainder part. And what I should get after the long division is x divided by 4. So I'm going to label this a 1. Do long division to fix it. Another option, which we're going to do here, is we're going to build it with the assumption of a slant asymptote. So let me show you what that looks like. I know I have a slant asymptote of 1 over 4x. So I'm going to write h of x equals 1 over 4x, or x over 4, plus, so that's going to be the whole part. What has to come next is a fraction part. And I don't know what number goes on the fraction part, but I do know that I need to have a vertical asymptote at x equal to 0, which means I need to divide by x. And the reason this is going to work is because once I find a common denominator and everything, I'm going to have a single fraction, and I'm going to be able to solve for what this number is. So instead of using the dollar sign, let's go ahead and change it to be a letter. Let's call it C. So let's see what this common denominator looks like. This is going to be, needs to be 4x. So we need x squared over 4x plus 4c all over 4x. And when I combine these, I'll get x squared plus 4c all over 4x. Now, either at the very beginning or at this step here, I need to fix my coefficient so that my x-intercepts are true. Based on all the information I have on here, I can actually just compare it with my previous work. But I'm going to get the answer of c equal to -1. So my final answer should start looking like h of x equal to x squared minus 4 all over 4x. But what this is missing still is it's missing the whole at x equal to 4. There's nothing in my answer down here that is preventing me from plugging in x equal to 4. But I know from the graph that if I plug in 4, I should get something which is undefined because I have a hole there. So what I'll do is I'll just multiply top and bottom by x minus 4. And now I have a function that has a hole at x equal to 4. It's really that easy to include. So let's go ahead and compare that with what I popped into the graph here. And that won't move, so that's great. Perfect. So I'm saying my h of x is x squared minus 4 times x minus 4 divided by 4x times x minus 4. And when I put in was actually exactly that. I have x squared minus 4 times x minus 4 all over 4x times x minus 4. The x squared minus 4 part gives me my x-intercepts at plus 2 and minus 2. The x in the denominator gives me my vertical asymptote. My 4 in the denominator is partially a result of trying to find the correct coefficient that will give me a slant asymptote of 1 over 4x after I do polynomial long division. And I multiplied top and bottom by x minus 4 because my graph has a hole at x equal to 4, and so I added those so that my original function would be a version that excluded that. Next week I will have a set of problems lined up for you to work on with your groups, and hopefully by that time the Zoom and Canvas will be fixed so that you can just start up a group, I guess a group meeting with your group members that way.